Okay, another quick one today, trying to solve the MRI question of why does the MRI pick up protons, and strictly the proton itself is the nucleus of hydrogen atoms. So it's picking up the nucleus of hydrogen, and it looks for a polarity to that nucleus, whether it faces north or south. Let's call it that. All right, and here's what they say. Why do more protons align themselves parallel than anti-parallel along a magnetic field in that MRI? Because they blast it with a magnetic field like crazy. And you know how that lines things up in a line like the, well, they call it magnetic lines of flux, and they put iron filings down. You see how that works. Now, everybody knows that. So why do some go align themselves parallel to them and other ones anti-parallel? So opposite to them. Well, then they come up with this reason, and it is, I know that it is surplus parallel protons that when energized by a radio frequency, so there's surplus parallel protons, let's talk about that in a minute, when energized by a radio frequency pulse, move to an anti-parallel state. But why is there that tiny percent more parallel than anti-parallel in the first place? Does it have something to do with the fact that the anti-parallel atoms have a higher energy than parallel? Yes, my friend, it does. Let's see why. And it goes on here, and this guy, Rupert, 1920, had it dead nuts. He is exactly correct. He says, is it because of a higher energy state? Yes, absolutely, precisely. He says the phenomenon is known as the Zeeman effect. And I looked into it, and I believe he's exactly correct. Because there is a very slight energy difference. Now, that is where I come in. Why? Under thermal equilibrium, there will be a population difference between the two states, thus giving rise to a net magnetic moment. All right? Magnetic moment is the centers of positive and negativity, and that gives you a magnetic moment in a molecule. Now, I know that it is surplus parallel protons. Anyway, the rest of it goes on. I don't fully understand what he's talking about. Actually, a common misconception, radio frequency pulse doesn't flip any of the nuclei spin down to spin up. I'm going to show you how I take this. He's talking about how it rotates the magnetic moments of the nuclei, and it does. But why? That's the key. Why? And I think I understand why. All right, there is a ton of possibilities here, but let's start with normal and why they're looking up at parallel against non-parallel. And what does that mean? It means laying flat would be this water molecule, oxygen, and two hydrogens. What happens? The oxygen needs electrons, and the hydrogen just happens to have one of each, and the oxygen needs two. So it says, let me borrow these, and they say, all right, we'll share them. So they put it on this side of the hydrogen. That means this side of the hydrogen is positive. That means the oxygen takes on an additional negativity, so this side becomes negative. That's what's called a polar molecule. It has centers of positive and negativity, positivity and negativity. And they call them magnetic moments. There's all kinds of stuff. But just think about it. It's a little tiny bar magnet, that's all. Now, and that is normal. That's normal water. Now, what else can happen to water? I think it could have an extra hydrogen. All right? I don't know exactly why. What in the core would change that, but I know already the cores are wrong. So there might be additional, because I say that there is no neutrons ever, never was. The cores are flooded with the positives, are flooded with the negatives until they can no longer absorb negatives. And at that point, they take on a tiny additional negativity, and that keeps all the other negatives trying to get in their orbits until it goes far enough out where they lose contact with reality. So that they have their valence shells case closed. Now, but the plus will always try to attract more stuff. It just does. But the negatives can only get in so far, and then they repel the incoming negatives until they reach a basic stability. Now, I believe there's something different about this core which attracts an additional positive. I mean, this is just a hypothetical. An additional hydrogen, which the hydrogen now turns around, because the negative side will be here, pushed away, and the positive side will be here, because this already has an additional negativity, and I believe an additional negativity from the core, pulling the positive, leaving the negative out, and pushing it away from the other hydrogens. That is my expectation. That is a half an integer in my mind. That would lay this thing sideways against that. Maybe. All I could say is I'm just fishing around. But this, because these things don't always come up with this two protons case closed. No, absolutely not. They have different configurations in the nucleus. Already they know that. But they just say there's more neutrons or there's less neutrons. But there's always, except for hydrogen, the same number of protons in the nucleus as there is in neutrons, or there is additional neutrons, which means additional negatives. There's no neutrons. So they always have enough to cover themselves to become negative. And as soon as they can become negative, they repel the incoming electrons. As simple as that. That's how orbitals work. Now, let's take another case of how this could possibly occur. All right, now remember this. This is called the Zeeman effect, and it shows these magnetic fields. And that's what they are flooding these people with. These kind of things are just smashing all over them. And then they're picking up the response to the particles that are in the body to these fields as they pass by. Now, and this is what they talk about. It's the several components of the present static magnetic field. It's analogous to the Stark. It goes on about a bunch of stuff. But remember this stuff, these circles. Those are what's coming down, and they are, and like it says, the spectral lines of mercury vapor lamp showing anomalous Zeeman effect. Without magnetic fields is this one. See, there's no magnetic fields wrapping around the interaction. You know, it's hard to explain, and nobody else can explain it either. So don't think I'm stupid because I can't explain it. But I can. I know what's going on. I just can't put it into words. These are the separations between the. You stay away from me that far, I'll stay away from you that far. As they get further out, there's less and less of a distance between them because they're less and less attracted. But in the inner core, they are pushing each other away because there is more of attraction, which makes them more energetic. That's what I see. Now, these are not showing any magnetic field lines around the actual center of the field flux line. These are showing the magnetic field surrounding, only they're bigger, and they push against each other. And that's why they stay, and I will show them on ours, because I show them. And they're not only just like these little tubes around it, they are particles surrounding it. Actually, they're particles going this way, not going this way. And then they show a separation. I don't know exactly what that's about. But anyway, I'm going to show you how this Zeeman effect plays out, and that is what they're looking for. They call dipoles and all this stuff. But the true effect of the thing is they're looking at these waves come through matter, and what did these lines stimulate? Did they stimulate something to go this way or that way? And then they look at it. Apparently, somehow, they can tell from the feedback of this. I mean, it's a pretty sophisticated machine, whether it's this way or that way. All right, I'm going to be referencing the right-hand rule, and I probably have already, but this is the demonstration of the right-hand rule. The particle is this white dot spinning to the right, drifting to the left. That indicates a spin to the right. You see the compression at the top versus the openness of the wave at the bottom. That is because it just came through the accelerator here, and it is now compressing as it's hitting solid space. Now, my contention is that is a particle, like this is a particle. It is spinning through space like this, which causes it to drift. Now, the wider the frequency, that's a wave. So they always, it's a wave, because they see this. But it's a particle, so let's go with both of them. Let's give everybody a pass on this one. So there's your wave. There's your particle. So this is the trajectory. It's not just something that's flowing through there. The particle is spinning through space. Now, and I can show that in another extremely well shown. But before I do that, I want to ask anybody that has a gyroscope. What I want you to do is spin the gyroscope in both directions. Try to see if it goes clockwise or counterclockwise. Is there a difference? And please, I want to know what that difference is in the comments. Thank you. All right, this is about as clear as it gets. A machinist would see this here, and he would say that is a drill bit coming at you. Well, it's a right-hand spin. We're looking down at a pattern on a box, a backboard. The pattern made by a single slit, I believe, was a single slit of the Venturi, and here it is spinning like this. Here's the particle. If it comes over the top, it falls back in here, so you see it as dark, and it falls down under, behind, and you see this pattern. If it comes around and the particle enters from the underside here, you see them splay out on this side. So most of them go straight through the center, but some, well, you saw what I saw. Because some go that way, and the other ones hit going and coming this way. So it's either way, and it's just screwing right through there. You can't hardly miss it. I mean, there's no way I can explain it any better than that. All right, I showed the Zeeman effect. For, that's what they say happens, and here's exactly identical what they're saying. These fields surround a tiny, tiny, tiny particle, which in the Higgs boson range, they call it a charge carrier. And these little tiny white filaments are the charge carrier particle that comes through the air. It's called a boson, and it is surrounded by a field strictly like just throwing your fist right through the air. That is what gives it mass, is its collision with the air. And this interaction with the magnetic pushback by these tiny little particles to form these circular rings, because they oppose each other and they force each other into these beautiful little patterns. You see how cute they are? That is that's Fibonacci. And it's just an absolute fact that's going to happen because they have this push against each other. And so these are what they call the Higgs fields. And that gives this little tiny bitty thing in the center mass. And the harder it hits something, the color changes. These are coming out of here all kind of different frequencies and mass, because the frequency is the mass. These are accelerated above the speed of light. Einstein had everything wrong. I'm telling you this right now. This is a fact. I'm sorry, Albert. God bless you, but you got it wrong, pal. Now, when they come out of here, they're highly accelerated Cherenkov radiation. It came through a Venturi. Rod Warren discovered this. It was actually totally accidentally. He was just playing around his garage, and boom, he comes up with this. Now, and when I saw all these pictures, I went freaking crazy, because I knew exactly what he had. And this is it. These are bosons. These are particles. And this one here is a highly, highly, highly accelerated, energetic, and possibly spinning backwards particle. That I don't know. If it's spinning backwards, I would really be interested in that. And coming through there, spinning backwards, it would create just a hell of a lot of push against everything, because they won't spin backwards. They refuse to spin backwards. It's called the right-hand rule. So that's a possibility. That's which I just came up with, about an hour ago. I'm telling you, this is a flow. I'm not throwing this out and saying, I know everything about this. Absolutely not. I have things to discover. I have things to show. I just look at things. I'm no big hero about this. I look at things and I think about it. I don't just dismiss them. And that is the kind of pushback I get from the mainstream scientists. They are happy, deluded. Perfectly happy, deluded. What is that? Initials. Anyway, that's the case. They don't want to know. And I think this might be spinning backwards. I don't know. I just don't know. But I can show you what happened when it crashed into one of these. And it's this. Hold on. I was really having a hard time with this, and I think now it is a backwards spinning particle. That's the only thing I can think of. How could it be so energetic and presents such a small magnetic field surrounding it? The counterclockwise spin of the right-hand rule accounts for a hell of a lot of electronic interaction. It makes everything spin easy. Spinning easy, easy, counterclockwise. You try to go clockwise with electricity and you will not get there. It just won't go. Won't go. It's called the right-hand rule. And I think this puppy here coming through that accelerator somehow got zipped backwards. And it's just saying, oh, what am I going to do? And it finally smashes into this thing and says, oh, thank God. And it turns around and creates this and whatever's going on there. I don't know. You know, who knows this stuff? I don't know this stuff. All I can see is what I can see. And you can see what I can see, so we see what we see. Somebody should see it too. You know, people that are supposed to be concerned with this, but MIT, Stanford, none of them. Nobody returned my calls. Nobody returned anything. Any of the professors, none of them. And any of the, I mean, I'm not just pointing them out specifically, although that I did contact them, and I contacted all the other ones too, because this is important and nobody cares. So, I think you got to take it into your own hands and say, just come up to Mud Fossil University and find out what reality is. And you take it for yourself. If you don't like it, just go on about your business. You didn't lose anything. I don't judge you. I don't tell people that you're not worthy of going out and making a living because you didn't remember what I told you to remember, even though it's wrong. You know, this is things just got to change a little bit. You know, we got to change the names to protect the innocent.